Welcome back to Chemistry Clubhouse. Today we're going to talk about a type of reaction, so in this case single displacement reactions, and then we're going to look at taking that single displacement and making a net ionic out of it, and then seeing what is actually reduced and what's oxidized, so a redox reaction. So there's a lot that's going on in a single equation. So let's get started. Let's take a look at this following equation. So 5 grams of aluminum metal is reacted with a solution of nitric acid. All right, so let's write out a simple balanced equation. All right, so we have aluminum, which is going to be a solid, plus nitric acid, which is HNO3, and then that reacts to form aluminum nitrate. So again, that guy's going to be a +3. This is going to be a -1, so we need 3 of those, plus H2. All right, now if we go through and balance it, again, that hydrogen gas is going to be, that hydrogen is going to be a gas. You don't have to put the S's and the G's, but for our cases, it makes it a lot easier once we start doing the net ionics. Okay, so aluminum is a solid, reacts with this nitric acid. We have 1 nitrate on the left and 3 nitrates on the right, and then 2 H's on the left and 1 H on the right. So it's going to end up being 6. So we have 3 H2s. That's going to be 6 nitrates, 2, and then 2. All right, so hopefully we've gotten good at these balanced equations. Okay, so this is our balanced equation that we're going to work all of our dimensional analysis off of. Okay, so this is first, and then let's look at how we would write a net ionic for this. Okay, so to do this, we need to look at everything. We need to say, what is it? Okay, so this guy right here is going to remain as 2 ALs, and that is going to be a solid form. This HNO3, this guy right here is aqueous because we know that that's dissolved in water. Okay, so how that's going to break up is this right here, all right, so this, the 6H of the HNO3 is going to be 6H plus. And then the 6 NO3s is going to be 6 NO3 minuses. So I've got all of those because HNO3 breaks up into an H plus ion and an NO3 minus ion. All right, now we go to the opposite side and we look at AlNO3,3, and we got to decide, is that a solid? Does that precipitate out, or does that remain in aqueous solution? So we know from NAPS, our little acronym, NAPS, this is NO3 minus, this is NH4 plus, this is K plus, and this is Na plus. Those are always soluble. So anytime those are in a compound, they're always going to remain in solution or remain in an ion form. And since we look here, we've got NO3 and we've got NO3. What that tells us is this guy right here is going to remain in aqueous solution. So that tells us here we're going to have 2 Al pluses plus, now this gets tricky because we got 2 and 3. So that means we have 2 AlNO3,3s, which means we have 6 NO3s. So that's going to be 6 NO3 minuses. And then H2 is now a compound. So if you remember from bonding, that's going to be H bonded to H, and that is a covalent bond. All right, so that just stays together. That's going to be floating off into gas. All right, so that's going to be our gas. So this would be considered our complete ionic. All right, so this is our complete ionic. Okay, now The cool part is with a complete ionic, we can get rid of anything that we refer to as a spectator. So if you notice, this 6NO3 and 6NO3, it was in solution on the left side before they reacted, and it was in solution on the right side once they've all reacted. So what we can do is we can just cancel that. All right? And that's what we refer to as a spectator. And more specifically, a spectator ion. So that's gone. Now if you notice, this Al and this Al are completely different. This is aluminum, all right, in a solid form, just like you would see with aluminum foil. This is aluminum in its ion form, so it's dissolved. You wouldn't even see it. It would be in the water, totally gone. This hydrogen is the hydrogen that floats around to make pH. Okay, this hydrogen floated away in the gas state, so they are nothing the same. So the aluminums and the hydrogens have changed completely. So what we do is we say those guys are going to remain to make what we refer to as the net ionic. So now our net ionic is going to be what's left over. So we have 2Al solid plus 6H plus yields 2Al plus, oops, I forgot the 3 here, 3H2 gas. Now if you notice, if I do this correctly, the balanced equation and the net ionic equation will be completely accurate. So again, I have 2Als, I have 2Als, I have 6H's, I have 6H's. So I'm still correct. And now this is what we refer to as the net ionic, or more importantly, the equation that is actually happening during this chemical reaction. Okay? Now, in addition to that, because this is a single displacement, it's also referred to as a redox reaction. Okay, let's take a look at that. All right, so if we take this net ionic equation, we can actually look at all the charges. So if we have 2Al solid, that has a 0 charge. All right, and the reason why it has a 0 charge is because it's a natural state. It hasn't gained or lost any electrons. And we know that anything in its natural state has the same number of protons as it does electrons. Okay, whereas this H plus is 6H plus, it has lost its electron. So each H is a plus 1 charge. We go to the right side, oops, that 2Al plus 3, because it lost its electrons, I didn't write that on the last equation, but that will be a plus 3 charge, whereas 2H2, because it's also in its natural state, again, that's one of those diatomics. This guy is that diatomic, which is one of those 7, Br2, I2, N2, Cl2, H2, O2, and F2. So again, that Brinkelhoff or the Magnificent 7. All right, so again, that charge is a 0. Okay, so when we look at reduced and oxidized, the easiest way to do it is to just look at their charges. So if I look at aluminum, aluminum goes from a 0 to a plus 3. So by going from a 0 to a plus 3, it has increased its oxidation number. Whereas if I look at H went from a plus 1 to a 0. So that is a decreased oxidation number. Now, what's another word for decrease? Reduced. All right, so that's reduced, and this guy would be considered oxidized. So what we know is that when aluminum goes from 0 to a plus 3, that guy is oxidized. And then when we go from hydrogen plus 1 to a 0, that guy is reduced. Okay, so again, you're just looking at the charges. The key thing is, can you write the equations correctly? Can you identify their charges? And then can you see, Did it increase or decrease its oxidation number? And then that's going to tell you all about who's being reduced and oxidized, and then we call that a redox reaction. So let's go back to this equation. Okay, so we've got this reaction. We've got the aluminum plus the nitric acid yields aluminum nitrate plus H2. We've got 3 of those, 2 of those, 6 and 2. So again, what this reaction is going to usually ask is how much gas can I collect? Okay, so the question might be, how many milliliters of gas can be collected at 0.98 ATM and let's go 23 degrees Celsius. Okay, so this is going to be, we know that we have 5 grams of this, and what we're trying to do is how many milliliters of gas can that hydrogen make? So let's do a little stoichiometry. So we've got 5 grams of aluminum. We know there's 26.98 grams of aluminum for every 1 mole of aluminum. Now we've got to go from aluminum over to this gas. So we're in moles of aluminum, and we know that it's a 2 to 3 ratio. So let's write that. For every 2 moles of aluminum, there are 3 moles of H2 formed. All right, and that's all we need. All right, all we need is that 5 times 3 divided by 26.98 and divided by 2, and that tells us that we have 0.278 moles of hydrogen gas formed. Now all we need to do with that is convert that into liters by using our wonderful equation of PV equals nRT. So our pressure is 0.98 according to the question. Our volume we're looking for. Our moles is exactly that, our moles of gas. I don't want to know moles of aluminum nitrate. I don't want to know moles of nitric acid. I want to know the moles of the gas, and in this case, it's H2. So 0.278 moles times our gas constant, 0.0821, and then times that temperature, which is going to be 295 K. All right, and then we just calculate this out. All right, so 0.278 times 0.0821 times 295. We divide that by 0.98, and we get V is equal to 6.87 liters of H2. And that is our answer. Okay, so I hope this helps. Hope this shows you how to do a single displacement, net ionics, redox. All right, there's a lot of work that goes into this. But again, if you just practice those balanced equations and really pay attention to those charges, this isn't too bad. All right, good luck, and I hope to see you next time. Bye-bye.